In this video, we discuss the technique known as integration by parts. So let's say I want to find the area or volume, for example, bounded by a function y equals x e to the x, or say y equals x squared cosine of x. If we look here, these functions, if I'm finding the area or volume, I need to integrate these guys, right? And these functions have kind of two distinct pieces in each of them, an x squared and a cosine, an x and an e to the x, and they seem to be the result of some sort of product rule, right? We need to be able to integrate these guys to evaluate their integrals. And none of the basic rules or formulas that we know so far are going to help us here. But again, one of those keen observations is that we imagine that these come from some result of a product rule. So what we're going to try to do is go through where this kind of idea of integration by parts comes from and derive the formula for it. And it's going to come pretty much from the product rule. So we're looking for a way to integrate some function that looks like f of x times g of x, basically the product of two things, okay? And the way we set this up is we consider something like y equals u of x times v of x, okay? And the way we kind of go through this is we basically take the derivative of this function here, u of x times v of x, and then we kind of want to work our way backwards to come up with a formula for the integral of something that looks like f times g. Okay? So again, the first thing I'm going to do here is take the derivative of all of this with respect to x. Okay, and I'm doing this implicitly, right? So I'm going to see a dy dx on the left, but also from the right side, I see kind of like a first function, a second function, u and v. That's going to be a product. So I need a product rule here. Again, on the left, I have dy dx. On the right, my product rule gives me du dx times v plus dv dx times u, right? Derivative of the first times the second plus the derivative of the second times the first. So once I've got my derivative there, I want to manipulate this in such a way to kind of recreate, again, that integral I have in the first line of this slide. And what we notice is that there's a dx in kind of each denominator across the board here. So what we do is we treat this like kind of a separable differential equation. Okay? There's some things we kind of gloss over here, but what we are able to do is basically multiply this entire thing through by a dx. Okay, so like I said, there's a little bit of hand waving going on here, but the idea is that we distribute that dx through and we end up with just these differential pieces, dy equals v times du plus u times dv. Okay, now again, all of this is coming from the derivative of some product looking type function, and we have the derivative, okay? We know what the actual function y is. So the way this technique works is by kind of integrating from where we are now, where we've just arrived at. We are able to use the form of y to help us, again, come up with an integral that looks like the one in the first line there. So what I'm going to do is integrate each piece to recreate what I just blocked off there. Integrate each piece with respect to x, basically. And the way this is going to work is the derivative of y integrates to be just y. And each of these guys also has an integral in front of them, right? I don't exactly know how to integrate each one of those pieces just yet. But what I notice is that kind of both of those integrals then on the right-hand side look like f times g. They look like the product of two separate things, a v du and a u dv. Now v and u are separate functions, right? And their derivatives, du dv, those differentials are also separate things, right? So I've kind of got like four pieces parts, hence the name, parts. I've got four pieces there that, are making up two separate integrals. Again, we remember that y is equal to u times v. So let's make that substitution here and so show that uv equals the integral of v du plus the integral of u dv. Okay? Again, the goal is to find a formula for the integral of something that looks like f times g, or the integral of a product, basically. So what we do, convention, has us solve for one of these integrals, and the one that has us solve for is really u dv here. Okay? So that's what we solve for. So I want to leave that on the right side by itself, and I'm going to move this other integral to the left side, and I get the integral of u dv is equal to uv, and then I'm going to subtract the integral of v du. Okay? This is what is known as our integration by parts formula. Okay, now I know that was a bit confusing. It takes a little while for that kind of process and that derivation to sink in. I wanted to show it to you, and to also show you kind of where the pieces parts come from. Again, this f times g is really kind of what we see in here as u and dv. Okay. Now I want to put this to use. I'm going to do several examples for us in this video, all showcasing the power and the usefulness of this integration by parts formula, where we would use it, maybe where we won't, and how, depending on the situation, do we do integration by parts. So first up, kind of where I was leading with this video, is find the area under y equals x e to the x from x equals 0 to x equals 1. Okay, we know that we find area by an integral as long as our function is positive on the interval that we're working on, right? And x e to the x is always positive between 0 and 1. So I don't really have to worry too much here. I set up my area as the integral from 0 to 1 of x e to the x dx. Okay, and I notice this integrand, x e to the x, has two entirely different pieces here. The way we work through this is we set up a u and a dv, okay? Because that's what I want in my integral. I want the integral of u dv to be equal to, we have that uv minus the integral of v du. So I'll write this all down. I've kind of underlined what I'm thinking about already. I'm going to take u to be x, and dv to be e to the x dx. Okay, dv is always going to have a dx in it, or a d, whatever your integrals with respect to, but there's always going to be that differential operator there. So what we do here, we know from the formula on the previous slide, I'm also going to need du and v, okay? Du is the derivative of u, and I just get a dx there. V is a little bit more tricky. V is the integral or antiderivative of dv, right? So for us, that is the integral of e to the x. So to go from dv to v, I'm taking an antiderivative, right? And that's getting me that e to the x. Okay, so that's an easy thing to forget, but I have to take an antiderivative to get from dv to v. Okay, now I can work a little bit towards actually figuring out what this area is. U dv in my integral there is equal to u times v. So u is x and v is e to the x minus the integral of v du. Okay, I have v now and I have du, so I'm really just plugging those in. V is e to the x and du is dx. So really what I have here then, when it all is said and done, I have u v e to the x minus the integral of e to the x dx as this new e to the x in purple there. And it's being subtracted. And I need to evaluate all of this then from 0 to 1. So I kind of forgot that as I was looking through my integration by parts, but indeed this is a definite integral, right? So those bounds have to come in at some point, and I've shown how we typically write those in a scenario. what happens most often is that, like I said, you forget about them and then you work with them at the end. Okay, so I need to plug in 1 and 0 and subtract the two in my antiderivative there, x e to the x minus e to the x. And of course, the first thing I notice here is there's an e to the x in common. Now, if I can simplify an antiderivative before I evaluate, things are going to be a little bit easier, a little bit more straightforward. So I'm going to kind of erase what I have in my brackets there and factor an e to the x out, and I end up with e to the x times x minus 1. Okay? Now, plug in 1 for x, I get e to the first times 0. Plug in 0 for x, and I get 0 minus 1 is a negative 1 times 1. Okay, that's subtracted. I get 0 minus a negative 1 should be 1 for that area. Cool. Interesting type problem here. And it uses what we learned in chapter 7 to, talking about area, but now with a new technique to be able to integrate something that we wouldn't have been able to integrate before. This is just one of the kind of the types of integration by parts. I'll showcase a few of the others. Next, here, I want to evaluate the integral of x cosine of x dx. So kind of the same thought process here. I'm looking at the integral of u dv, okay? Now, when I set things up here, I'm pretty much just going to try to do them the same way. So far, I've let x be u. So I'm going to try that again here, and dv then is just the leftovers, right? So dv will be that cosine of x dx. One thing you have to pay attention to is if you can take the derivative and take the antiderivative of u and dv respectively. Okay, so that'll kind of be an indicator as if you've chosen the correct pieces parts. They're not always going to be nice, pretty order. But so far, so good. This has worked for us. I've got u equals x, so then du is dx. If dv is cosine of x, antiderivative of cosine is sine. So my integral of x cosine x dx I can write as, and the way I like to do this, we know it's uv. If you set up that little table in the upper right corner of my slide, I can always do this multiplication. U times v is uv. So I like to draw that arrow to help me remember that I'm taking u and multiplying it by v. That's x sine x. Cool. Minus the integral of v du. That multiplication shows up in the bottom row. If you always draw your little chart this way, it shows up in the bottom row as multiplication from right to left. v du, which is sine of x dx. Okay. That part always goes in the integral. It's very easy to forget that you have to integrate again in this process. Okay, so you're always going to integrate dv to get v, and then you're always going to have to integrate v du later on. Okay. So simplifying, I can actually integrate sine of x. That's really the only part of this that's going to change. I've got uv minus the integral of v du. So that formula is right there, kind of playing along with it every time. Just copying down now, uv is x sine x. I can't simplify that much. Minus antiderivative of sine is minus cosine of x. And of course, I have an indefinite integral this time, which means I need a plus c. Simplify just a bit more, I can add minus a minus cosine is plus cosine, and that's pretty much all I can do. No real factoring or anything needed here. So, relatively basic integration by parts here. I've got an x times a cosine, two completely different functions that I can't really rewrite or simplify in any way. This is where integration by parts is going to shine. Okay? I want to make a note here, and that is if I change this problem a little bit, we aren't going to use integration by parts. We would not use parts to evaluate something that looks like the integral of x cosine of x squared dx. Okay, and that's because I can just substitute, right? If u is x squared, du is 2x dx, I've got substitution. So a lot of times when students learn integration by parts, they tend to forget those other basic rules, and this is why I'm saying this here is as a reminder, don't forget about u substitution and the basics, okay? It's very easy to do. Not everything from here on out is integration by parts. There's still some really basic, straightforward integrals that use the basic formulas. So make sure you have those down. And if you have those down, integration by parts and the sections that come after this are just going to be that much easier. Something a little different here. Integral of x natural log of x dx. Okay, so same game. I've got x and a function times dx. I'm integrating. Let's try the same deal. I let u be x and dv be natural log of x dx. Okay, cool. Du is dx as before, and dv is the integral of natural log of x. And I don't actually have any clue what that is. What is the integral of natural log of x? It's tempting to say 1 over x, but no, that's the derivative. We don't actually know the formula for the integral of natural log of x. In fact, spoiler, you need integration by parts to find it. Okay? So the way we've got our integration by parts set up right now, we're kind of stuck. We can't go any further. Okay? In a situation like this, you've kind of just going along with things. You've chosen a u, you've chosen a dv. You go about, finding du and v. If you have trouble with that, if you can't find a derivative, now that doesn't mean just because of going from u to du is difficult. No, it's just impossible for us here to go from dv to v. We don't know the formula, and it's not something that yes, you could look it up, but when you're in a situation like this is when you want to try switching your u and your dv. Okay, you've kind of maybe chosen incorrectly. So I'm going to erase some things here, and I want to kind of retry. So let's get rid of all this, and I'm going to switch. So my u is going to be natural log of x, and my dv is going to be x dx. Okay, so now du, derivative of natural log of x, is that 1 over x dx, and the integral of x is 1/2 x squared. Okay, both of those I can do pretty quickly, readily available. Usually integration by parts, when you're finding du and v, they're basic formulas. There can be some hiccups in there. Finding du might need a product rule. That happens. There's other things that might happen when choosing u and dv. But for the most part, there's basic integration and differentiation rules there. So I'm going to bring things together here. I know now that the integral of x natural log of x is going to be u times v, this multiplication, natural log of x times 1/2 x squared, minus the integral of v times du. So I've got 1/2 x squared times du is 1 over x dx. Cool. Things are going well so far. Okay. Now, just a little rewrite here, and also I'm going to try to simplify this guy here. But what I want you to pay attention to is that when we simplify that and rewrite our second integral there, that should be something that we could integrate as well. Okay? So for integration by parts to go the way we kind of want it to, you should get to this point and still be able to continue and then integrate your v du. Okay? So, rewriting things a little bit, I've got something like a 1/2 x squared natural log of x minus, and I've got some cancellations there. X squared cancels with x to give me just an x. And I'm going to bring a 1/2 out here, and I just have the integral of x dx. Okay, pretty straightforward. Integral of x dx, and that's something I actually already did. Going from dv to v. dv to v, I found the integral of x dx. So, simple basic formula here, 1/2 x squared natural log of x minus, I'm going to get another 1/2 when I integrate x. I've got 1/4 x squared plus a c. Okay? That is usually pretty good enough for me. However, we do notice that there's an x squared in common here. And I can do even better. I could pull out a 1/2, but watch what happens when I factor out a 1/4. There should be a 2 natural log of x minus 1 then in parentheses. Right? And that's a nice, pretty cleaned up form of my antiderivative. Like I said, this guy is kind of the formal correct answer, but I often take this. So now I want you to try something else. Integral of x natural log of x squared dx. I'm not going to cover that in the video here, but just as kind of an extension of what I was talking about on the previous slide, maybe I want to use some other techniques. Maybe a substitution I see right away. Give it a try. See what you come up with. The next example I want to do is a little different. The integral of arcsine of x dx. Okay. We know the derivatives of arcsine and arctangent and arccosine, but not the antiderivatives. And that's because the antiderivatives are going to require use of integration by parts. These are a little tricky. They are a little cloudy on the pieces parts that I'm going to use. And in fact here, like I said, I know the derivative of arcsine, so that's actually going to be my u, and my dv is just going to be dx. Okay? That's legal. I'm allowed to do that. Usually there's something else with, that dx for dv, but there's nothing else in my integral here. So arcsine, is my u. That means du, derivative of arcsine, is dx divided by square root of 1 minus x squared. And antiderivative of dx for v there is just x. Okay? So my integral of arcsine then is equal to uv is x times arcsine of x, or arcsine of x times x, minus the integral of v du. So minus the integral of x times dx over square root 1 minus x squared. A little gross, but I think it's still manageable. Again, our integration by parts is working if we've gotten here so far with no hiccups, and if we can continue with the integration. Okay, so rewriting a little bit, I need to be able to integrate this guy. I notice that I can substitute 1 minus x squared with u, which means du would then be minus 2x dx. So then substituting x dx, I would replace that with minus du over 2. That's just a substitution. Not so bad. Looks worse, but it is just a u substitution. Rewriting, I get x arcsine of x. And here, I'm plugging in a minus du over 2 for dx. So that minus outside the front of my integral here is going to change to a plus. I get a 1/2 on the outside integral, and replacing all this, I'll end up with I already handled the minus 1/2. I'll have a du over square root of u. Okay. And that's a basic antiderivative, just requires a little bit of rewriting. Integral of u to the minus 1/2. And again, it's minus because that u in the radical is in the denominator. Okay? So far so good. Now, take the antiderivative of that u to the minus 1/2. Keep my x arcsine x plus 1/2 antiderivative of u to the minus 1/2. I add 1 to the power, right? That gives me a positive 1/2. Divide by the new power. Dividing by 1/2 is the same as multiplying by 2. A little simplification. I see 1/2 and 2 cancel to be 1. I'm left with x arcsine of x plus the square root of 1 minus x squared. All of that plus a c. Cool. So a little different, right? This and the previous example, that x natural log, they didn't kind of really fall in the same category as the first two examples I did, x e to the x and x cosine x. Okay, so that kind of implies that some of our techniques may be different depending on the integration that we get. I can summarize this in some strategies for you. Strategies for integration by parts. Number 1 here, what I kind of want to try to do is we often try dv as the most complicated but integrable portion and let u be the rest. Okay, remember that choosing a dv means that we have to integrate it to get to v. And that can be tricky, but also it needs to be possible. If it's not possible with usually one of those basic formulas, then you probably got things set up maybe backwards. So that's one of the first strategies we try to use. Number 2 is that try use the simpler portion, or the portion that terminates. And the way I typically think about this is, for example, e to the x does not terminate, but x cubed does. So u in a situation like that would probably be x cubed, right? Because eventually it's a little simpler, first of all, but it also terminates if I take a couple derivatives. Okay? Number 3 is really when we start getting into the more explicit kind of guidelines. Number 3 says that the integrals that look like these, x to the n e to the x to the n sine x, and x to the n cosine x, these are all situations where you should choose u to be whatever is out front, that x to the n. Okay? If you can't do a substitution, I know I've got just u here. I'm trying to say that dv would then be the rest of those there. But if I can't do any other basic methods here, and I see one of these 3 types show up, your u in integration by parts would be that x to the n. Okay? Then dv would be the rest, and you can go through things pretty easily from there. Number 4 describes the last 2 examples we did. If you have integrals that look like x to the n natural log of x to the n arcsine, or x to the n arctangent, you're going to let u here be the other part. Okay? U is either natural log, arcsine, or arctangent of x. Okay? Then dv will be the x to the n part. Things will work themselves out. It's just these might be a little bit trickier. They're not as friendly or as straightforward, but they are doable, and it's not really so bad. Okay? So those are not quite all the scenarios that we see with integration by parts, but kind of the main subset of situations that we're in. Try some more examples and explore a little bit more. Start to get comfortable with these techniques. We'll continue to use them kind of through the rest of the semester. Thanks for watching.